Good morning, dear participants. I warmly welcome you to day 4 of the iTech program. We are about to start the first session of the day. It will be on the topic Understanding Power and its Sources of Emission. This will be delivered to us by Professor Priyanka Kaushal. Ma'am is here.
Thank you.
Ma'am, you can take your time now.
Yes, thank you, Emily. Thank you very much. Let me just share my PowerPoint. Yes. I think it's visible to everyone. Emily, is it visible?
Yes, ma'am, we can see it.
Okay. Yes, thank you. Yes, so in the process of the coursework, we are about the 4th day today. And so far we have talked about the various forms of energy, how it is generated, and what are the point sources where the emissions could be released, right? So all the emissions. Today, what we are going to study is we will understand the various sources of power, primarily based on coal, hydro, nuclear, and some of the renewable options as well, which are commercially used, and where from the emissions are coming, right? Because the whole course is about, it is designed in context of climate change and the role of energy there, and we are also looking at the carbon neutrality part of it. So therefore, it is important that we understand the sources of emission, because sources of emissions are very pivotal, especially when we do the GHG emission of per unit of power which is produced. That's the whole idea. The whole course, we are trying to understand the various fundamentals, the nitty-gritties of the emission part of it. Emission in terms of GHG, emission in terms of the energy that it has embodied. Any commodity, any unit, any process that is there in the entire supply chain, how much amount of energy it is consuming, and how much amount of carbon it is emitting or embodying into itself, or it is emitting GHG emission that is happening. So all that what we will be studying today. I'll start with understanding the various sources of emission, and then the following class, after the break today in the morning session itself, we will see how to calculate the embodied carbon and the embodied emission or the embodied energy for a coal-based power plant. So we'll try to get into the technicalities of it, try to keep it a bit simple as it can get. And then we will try to calculate these emissions, kind of a hands-on thing. Right, so let's start with, to understand the point sources where from the emissions might come from all these fuel-based power plants. Let's start with coal. But this is a global picture. If you look at the 10 largest power plant in the world in terms of their capacities in gigawatt, this is how it looks like, right? So the top 10, among the top 10, it's all hydro, with an exception of this Kashiwazaki power plant in Japan, which is nuclear. Right, the biggest capacity here, as we can see here, is the Three Gorge Dam, which is in China, and it has a capacity of about, if I'm not wrong, it's about 22.8 or 22.3, something like that. It's about, roughly, you can say 23 gigawatts capacity. And as you can see here, the second ranker here itself is like, it's almost half the capacity, right? So it's a huge capacity, and it's hydro. It's a hydropower power plant. This is how it is. It looks like in terms of their capacities. So Three Gorge Dam is like way too big. And then in the list, we also see that there is a very huge nuclear facility available as well. Normally, nuclear plants are relatively smaller in size with respect to hydro-based system, or to an extent that even coal-based system. But here we see a very large capacity nuclear-based system, which is there in Japan. So yeah, let's now look at the coal-based power plant, because still the world is using a huge amount of coal for the production of power. And this is a typical, very simplified diagram of a coal-fired power generation plant. And we see that these are various processes, right? I mean, these are major processes that I have put across. If you work in a power plant, or if you have seen a power plant, and if you go and see the PNID, which is process and instrumentation design diagram of picture of any of these power plants, you would see how complex it is and how many units are involved into it. every process. For example, if you look at second, which is generator, even in this generator there are multiple controls that are there for safety and security and for improved efficiency. So all those things, I have not brought in the PNID diagram here. It is just for simple understanding that this is how a power plant look like. And even if we leave apart the smaller units, smaller doesn't mean that they are not important. The bigger ones that we have been studying right from our school, there are obviously about 18 such things. We have a cooling tower, a generator, a low pressure turbine, there's a condenser, intermediate pressure turbine, high pressure turbine, all these different types of turbine, so that depending upon the pressure of the steam after it goes through one cycle and other, we could extract out more energy from it, or we can extract out more electricity from it, right? So at high pressure, there is a high pressure turbine. When it is released at a medium pressure, then it is used to run the second set of turbine, then the third set of turbine. All this to ensure that whatever steam which is generated in the steam generator, maximum of it could be converted into electricity, just to increase the efficiency of the overall efficiency of the power plant, because the job of a power plant is to generate electricity, right? So we use different kinds of turbines. And then there is a deaerator, there's a coal conveyor, coal hopper, pulverized mill. As you can see, these are all here. There is a boiler drum, there is an ash hopper here, superheaters, then there is an air intake, try to preheat the air here, and the preheater, as you can see it here, precipitators, fans, so on and so forth. All these units, now I have put up a boundary here, as you can see. Right? So when I do a life cycle analysis, the way we studied yesterday, this is a gate to gate. Right? So I'm doing from the coal which is coming in to the electricity which is fed to the grid. I'm not considering the mining part of it. I'm not considering the coal preparation part of it. Therefore, when we do life cycle analysis, it is important that we define our boundaries. Depending upon the boundary that we have considered, the emission that we load, or the carbon intensity that we load, or the embodied energy that we load on our product varies. And this is very important. So defining the boundary is very important, because and the boundary is often very eluding. So whenever we see a value, whenever we see a calculation, it is important to go back and see what were the boundaries that were considered, right? So, but since this course is primarily about emission points, so as you can see, coal-fired power plant, about 20% of the ash that we collect after the coal is combusted are particulate matters. And the impact of particulate matter, all these things could be quantified when we study the life cycle. Right? So we studied the life cycle very briefly yesterday. So all these are, and we also studied, we often hear that impact of coal leads to certain amount of death or certain amount of disease. How does it come from? How they are quantified? So there it comes from these numbers, right? And as you can see here, fly ash can travel up to 40 to 50 kilometers down in the wind direction. So in whichever direction the wind is blowing, it can have its impact up to 50 kilometers down the lane. And it may cause land degradation, air and water pollution to plants and animals, including human beings. And to an extent that they're even reported that in the milk that we collect from the farm, which are located in the near vicinity, the PM percentages are higher, right? That could lead to disease, not just to the animal itself, but to the one who are consuming it. So the impact of these particulate matter that are released from a power plant is not just impacting the health of, it's not just impacting the atmosphere, it has gone down to our food chain as well, right? And that could lead to lungs cancer as well. And if you look at these are what we are studying right now are the qualitative impact of it. And all these impacts are also quantified. The numbers are also given to it. It takes a very detailed analysis. It takes a long time to create these numbers, but we have some preliminary numbers with us. And these numbers are fed into these life cycle databases. And from there, we can read it and use it, sorry. Right? So yeah, so these are the impact categories of PM 2.5. It can lead to air pollution. It can lead to, it can harm the farm. It can harm human health. And it has gone into our food chain as well. that is about particulate matter, right? So when we try to see the impact categories, yesterday we talked about the impact categories. If something is happening, what are the categories under which it may cause impact? So these are the categories that PM can have its impact on. The next one is carbon dioxide, and we understand that very simple mathematics here, that the atomic weight of carbon is 12, and oxygen, as we understand, is 16. And when carbon and oxygen, that's what coal does, is combusted, it produces CO2. So ideally 12 grams, if you say 12 grams of carbon combines with 16 grams of oxygen to produce 44 grams of CO2. If there is a complete combustion, this should have happened, right? And then it is given in terms of pound, as you can see here. And if you look at it, coal with carbon content about 78%, typically that is the content that we assume, how much amount of heat is generated. And based on that, how much amount of CO2 can be generated, right? So you can see here, 1 ton of coal, and if I just look at it, 1 ton of coal can produce about 2.86 tons of CO2, almost 3 times, a little less than 3 times. So 1 ton of coal, so when you're combusting 1 ton of coal, you are actually emitting about 3 tons of CO2 into the atmosphere. And that is the reason, and this is the main source. The whole carbon emission, the whole the dirty business that is associated with the coal-based power plant is that this is the heart of it, right? So 1 ton of coal, 3 times CO2, 2.86, roughly 3, you can say, is the CO2 that what we are emitting. And this is the reason why we are now talking about the carbon capture and storage. That means you have to capture this carbon from the stack itself, from where it is released. And this technology, as you understand, is under development. It is too early to to say anything with lots of confidence in CCS. But one thing is for sure, when we are bringing in one extra step in the coal to power production chain, right? As a result of that, the cost will increase. And you are bringing in, right? Right now there is coal preparation, coal combustion, there is coal cleaning before that. So coal cleaning, mining, cleaning, transportation, this, and power. Now we are saying that emission and power. Initially it was like emission and power. Now we are saying emission, capture, power. So we are bringing in one extra unit here, or process in here, because of which it's very obvious that the prices would go up. And then we also understand, and it's multifaceted, right? And at the same time, there are other sources from which the production is constantly going down. Like if you look at solar, the way the price is going down, there is a challenge, right? So people will now try to move towards solar. And the way solar is progressing today, it's very likely that coal plant, we discussed in this COP26 about phasing out and phase down or of coal. Of coal-based power plant, right? So it is pretty much on its natural, it's on its path of being, if I may say so, on natural death, right? I mean, if it keep on facing such tough competitions from other sources which are renewable and cheaper, of course, that's where the market would go, and eventually it will die. The whole point is, should we wait for it to die naturally, or should we induce it? Things like that, right? So what kind of an mechanism various countries would take is of importance here. Next, from coal, of course, there is particulate matter, CO2. Next is nitrogen and sulfur oxide. So NOx and SOx, as we all understand, they convert into they lead to, I mean, when they go in atmosphere, they react and they form acidic compounds like sulfuric acids and nitric acid, and they get precipitated with the rain, which is popularly known as the acid rain. And yes, so that was about the acid rains, about the NOx and SOx contamination. And then there are some radioactive contaminants available as well. So you can see in coal, we have certain very, very, very tracer amount of impurities that are present in terms of uranium, thorium, radon, and other natural radioactive materials are available in coal. And when they are not properly treated, they can contaminate. They have the contamination effect on water and air as well. As you can see here, arsenic, for example, if it is dumped untreated, it can lead to skin cancer, bladder and lung cancer. It impacts the aquatic life. So So why I'm talking about all these impacts are because these impacts are quantified in our assessment tools. Whatever tool you are using, whichever software you are using, or even if you're developing your own model to estimate the emissions, the impacts, not just the emission, the impacts of certain action. So the action here is combustion of coal, right? So this is my action. Because of that, what are the impacts? These are the impacts. I'm just listing out the impact. The numbers for that are available in our data banks, right? And those data banks, some of them are freely available, some of them um, are paid services that we have to take, but they are there. We have some first estimate of these impacts available with us. And again, it varies from country to country, depending upon what kind of treatment mechanism they have put in place. I mean, if a country is capturing this arsenic, for example, and separating out the arsenic and then releasing the wastewater into the water body, then the impacts are relatively lower. But if you're not capturing, if a power plant is not capturing this thing, no, and it is directly releasing all the waste into the atmosphere, into the ecosystem, then the impacts are different. So we just, there's radioactive contamination. And the next here is the mercury contamination, right? And as you can see here, US EPA itself, they have reported that about 25% fish had higher mercury level than the safety norms. And these are the ones where they are next to the power plants. And the other research, as you can see, Stuttgart, University of Stuttgart found that the coal-fired power plant were the largest source of mercury air emission in the EU. And every country has come up with its own limit, how much of it that they can emit into the atmosphere. So EU has a 10 milligram per noble cubic meter per day. This much how a power plant can emit. China has also given. Japan has its own norm, and then that was the initial norm of EU. Now EU has revised this to 3 milligram. As you can see, 3 times they have lowered the emission that were permitted in terms of PM particle. This is PM particle that they can, particulate matter that can be released into the atmosphere. So various measures are being taken in place, right? So these are the sources of emissions coming from, but just from the combustion of coal. We're not taking into consideration the embodied combustion and the embodied energy of the coal-based power plant. It is on source, gate to gate, how much emission is happening in a coal-fired power plant, what kind of emissions are happening in a coal-based power plant. We're not quantifying it, we're just looking at the sources of emission. The next in the line is the hydropower. It's again one of the, they have a big share in global electricity market. And as you can see here, hydro-based power plant is based on a very simple philosophy, wherein the idea is to store the water at a height, and you have the turbine at or the turbine, whichever you call it, at a lower height. And when it is stored here, it is the potential energy of water, and you ensure that it acquires a huge amount of kinetic energy. It acquires a motion when it hits the turbine here, right? So the whole concept of hydropower is in construction of this dam. This dam could be done, it could be put to multiple use. It could be used to control flood, to meet irrigation requirements, so many things. But you need a dam. All the big hydropower plants need dam. There are run-of-the-river projects wherein we don't construct such dam. It is the natural gradient that is available. When the water is flowing, we take a slipstream for it, generate the electricity, and make the stream go back and meet the main river, right? But here we are looking at the dam-based system. If you're looking at big, the run of the river is possible only with small capacities. But when we are looking at big capacities, right, which runs in hundreds of megawatt, then we have to go for dam-based system, where you have to construct these dams. Okay. Now, if you look at, it certainly has certain benefits. Hydropower has a benefit, there is no doubt over it, and the benefit is relative. Like relatively in comparison to coal-based power plant, hydropower plants emit low. And this is because the fuel that we are using here is water, and it is almost free of cost. We don't procure it the way we have to go for coal. We are not mining for it either, right? And as you can see here, yeah, it is power of the gravity to spin the turbine, which generate electricity, and there is no fossil fuel burning. Since there is no fossil fuel burning, there is no stack emission, right? And that is the reason why and this precisely is the reason that the per unit electricity which is produced in a hydropower plant, the carbon footprint, the emission footprint are relatively lower. That doesn't mean that the embodied energy is lower, right? Please try and understand. So emission from its operation point of view, purely from its operation point of view, again, I'm talking about gate to gate, that the power is produced, the operation part of it. Since there is no fossil fuel combustion, there is no stack emission, it is very clean, right? In per unit of electricity generated from fossil fuel. With respect to that, it is a very clean option. And just a quick data, like if the hydropower plant was to replace coal, up to 4 billion tons of additional greenhouse gas would have been emitted per year. I mean, that the same amount of electricity which is coming from a power plant, if we replace it with coal, then additionally how much amount of carbon would GHG would have emitted into the atmosphere. But it is a very tricky business. Hydropower plant is a very tricky business when we talk in terms of the emissions coming out of the power plant. It is a cheap source of electricity for sure, because it does not involve the fuel cost. It is not sensitive toward the price change of the fuel, because as such, there is no fuel that we are procuring. It is the water which is stored, and then it is just the flow of the water by which we are generating electricity. We are not procuring operation part of it. There is no, like if you look at coal, if the coal prices goes up, the price of electricity goes up, unlike the hydro thing, right? So that benefit is there with hydro. But if our concern today is to look at how, if we are looking at how much emission is coming out of the plant, not from the business point of view, but purely from environmental perspective, if we are studying, then we have to see that whether the power plant that we are looking at is a green power plant or is it not. And it depends on multiple factors, right? As you can see here, water is stored also, but the reservoir where water is stored also produce both carbon dioxide and methane. And methane, as we understand, is about 80 times more potent in terms of GHG potential than with respect to CO2. That means if we say that if I score the GHG impact, the heating, to hold the heat and to hold the warmth of CO2 as 1, if I give that score as 1, then methane is 80. It's 80 times more, the potential of it is 80 times more higher than that of CO2. And just to give you a feel of it, if you have ever if we have seen those this sewage pipelines, and they have this manhole over it, and if you ever happen to stand in front of an a sewage pipe which has been opened, maybe for its cleaning purpose or for any of the emergency requirement, the gas that comes out of it, the air which is flowing across it, you could feel the warmth in it. That's what I'm trying to say, that methane, and because those gases are rich in methane. If it's a sewage line, if you're passing through nearby it, you would see that the gas which is coming out of it, you could feel the warmth. Your body can feel the warmth of that gas, and this is because CO2 holds. This is because methane, which is the prime gas which is coming out of those lines, the sewage lines especially, is known for holding heat for a longer time, right? So this was just in case if you have witnessed that, and this is because it is more the GHG the holding potency of methane is higher than that of CO2. And as you can see here, if there is a huge reservoir, if you look, it's a huge reservoir which is constructed here. It's huge. It's huge. It's almost the size of big lakes that you have seen, the biggest lake we could, and bigger than that actually, right? And since there is a water there, both carbon dioxide and methane is released when vegetation decomposes underwater. So here, some kind of microorganisms, other organisms also grow, vegetation also grow. And given that the water is stagnant, normally in a flowing water, the growth is not so conducive. But when the water is stagnant, it is very conducive. There is no friction available, right, at that point of time. So the vegetation grows, and there is almost like at a very faster pace. Let me put it this way: they grow very fast. So if that is the case, then they also decompose, they die. And when they die, they settle at the floor of the dam, and there they decompose. And when they decompose, it's very obvious, when they decompose, they are released in the form of methane and CO2. So if that is the case, then you end up releasing a huge amount of methane. All this is like induced impact. We don't want this to happen, but it happens. It has been observed almost in all hydro-based power plant, right? And therefore, you would see that there are enormous difference from facility to facility due to the range of varying reservoir feature and meteorological characteristic. It also depends. In cold countries, this may not be the case, but if you are living in a tropical, tropical nature, if the weather is tropical in your country, then this impact is likely to be high. So if you are living in a country which is close to equator, which is tropical in nature, vis-a-vis if you're living in Canada, for example, which is like primarily very cold country, then this decomposition thing the rate of decomposition will be very slow because the temperatures are very low in that country. But if you're living in a country where the average temperature is about 25, 30 degrees Celsius, 32, and it's very hot and moist and humid, then the rate of decomposition will be very high. Even the rate of vegetation would be very high, because those atmospheres are very conducive for life to grow, right? So that's why it is important that, so the decomposition data or the emission data which is available for Canada make no sense for a hydropower plant. Even if it's the same technology, it's the same company who has given it to you, it's all done by the same EPC company, but still the emissions would be different because of the different meteorological characteristic and the reservoir as well, the kind of water we have used, how frequently we clean it, so on and so forth. So all these things matter when we are looking at the net emissions which are coming out of the hydropower plant. But if we only talk about generation, only the generation part of the electricity, then it is very clean because there is no combustion which is happening. It's purely the motion of water which is generating electricity. This was one perspective. This other perspective, which also says that some hydropower reservoirs are actually carbon sink. That means they take up more carbon through photosynthesis than by organisms living in water that emit through their decomposition. Such data are also observed and reported, right? So what we all agree to this point, either this way or this way, that vegetations grow on these dams. Now, these vegetations which are growing, these organic molecules that are growing, if let's look and try and understand it from the organic point of view. Life, I mean, you and I, we are all hydrocarbon. So if these hydrocarbons which are growing in the form of life, like small vegetations, algae, for example, is another. So when they grow there, right? And since they are vegetation, they take up CO2 from the atmosphere. They behave plant-like. So they take CO2 from the atmosphere and they lock it. That is the process of CO2. So what they're saying that in some of the hydropower plant, it is also observed that these vegetation take up more, I mean, net, they died, they decomposed, and it is released back to the atmosphere. But they say that during the process of photosynthesis, they absorb more vis-a-vis when they decompose and go back to the atmosphere over the life of the hydropower plant. This is important, right? Over the life of the hydropower plant, how much they have taken up and how much they have released. So this is also reported that sometimes they may act as carbon sinks. So here they are releasing CO2 and methane. Here they are absorbing more CO2 and more methane. Right. In fact, of the nearly 1,500 plants worldwide, hydropower plants, they were examined and accounted for half of global hydropower generation. More than 100 facilities have greenhouse gas emissions that cause more warming than fossil fuel. right? So this is one of the report, and they examined 1,500 such hydropower plant in the world, and they found that out of these 1,500, 100 facilities were so that the greenhouse gas that were emitted from it were actually more harmful than the fossil-based power plant, right? So all these, as I told you, what the impacts are primarily coming from the meteorological characteristic and the way you operate your hydropower plant. Everything is accounted for. Technology may be same, it's the same company, it's the same technology that you are applying. I'm repeating it again, but depending upon the size. For example, I think it's the next thing, that there are things that can also be done when planning a new hydropower project. Therefore, hydropower project has the potential to either give you a green credit, and it also has a potential to give you an orange or a red certificate that you are a net emitter. And it all depends upon meteorological condition, as I told you, because operation part, try and understand operation part is green. There's no doubt about it. But before that, the storage part of it, it is the storage part of it which can take you to the green part of it, or it can take you to the red part of it, that you are a net carbon emitter, or you are a GHG, the net GHG emissions are higher. So therefore, planning of hydropower plant is very important, how you are doing it. So look at it. It says that there are things that can be done when planning a new hydropower project that can help keep emissions down. For example, if a facility draws from a large reservoir, if you have built a big dam, but you are generating a relatively small amount of electricity, it is likely to produce a disproportionately higher GHG emission. As I told you, it is the storage, it is the reservoir that decides whether you will be on the green side or you will be on the red side. Are you a green energy source or you are a emitting energy source, right? If you're a polluting energy source. And that depends upon the storage, that is dam. How is your dam made? How is your dam maintained? And what are the local conditions? So keeping this ratio in mind, it is a valuable part of the planning process, as their power density, we will discuss this power density later, has been found in the best indicator of overall GHG emission for a hydropower facility. So how much power it will generate. So the dam will generate, it has its certain nature. It will generate that much amount of GHG, less or more, whatever is the amount it will generate. Now, as I told you, in all these calculations, we do it per unit of electricity. That means it is generating, let's say, let's assume it is generating 100 kgs of GHG gas, and you are producing 100 unit, right? So the ratio is 1:1. So 1 unit of electricity, I'm releasing 1 unit of GHG gas, okay, or 1 kg of GHG gas. Now, if I start producing more electricity, instead of 100 unit, I have a very advanced technology, let's assume very sophisticated turbines, which can now produce 1.5 or 150 units of electricity. So this GHG is now loaded on 150 units, right? So it will immediately reduce my carbon footprint or my GHG footprint per unit of electricity. So this is important, right? So you have, therefore it goes hand in hand. Access to modern technologies, modern means efficient and relatively less polluting technologies, because when a technology it grows on these parameters or indicators. All the new technologies consumes less energy, that's how they become more efficient. And when they consume less energy, it very obviously means that they're emitting less energy, right? So it is important that you increase the power density. It's power and density, right? So increase the power density of your hydropower plant if you can. Temperature of the reservoir can also play a role in production of methane emission, and therefore avoiding development in extreme hot places could also lower emission. It is primarily because it is stagnant water. When you have a dam, you create a stagnant water. Water has a huge heat capacity. It can take a huge amount of energy into it. And if it is not flowing, if it is stagnant, the temperature is getting stored. And when the temperature goes higher, when it heats up, you can't reach to very high temperature, because then there is a night time which follows, then there is a daytime. So it comes to be in a thermal equilibrium and with that local weather. But if the temperatures are higher, we all understand that it leads to higher amount of methane formation, all the decomposition that is happening. Because when I talked about Canada and I said that they have this water hydropower projects and their emissions are relatively low because the average temperatures are low, but the atmosphere outside is very, very cold, because of which the methane emission and decomposition, the rate of decomposition of these vegetations is very, very, very slow with respect to a temperate or a tropical climate, right? So, and this is primarily because the water here is stagnant. So you have to ensure that as well. And of course, other than that, as I told you, operation part, there is absolutely no issue, no debate. It is very green, but all the debates are around the whole infrastructure, right? The change in hydrological flow regime, because you divert the direction of the river, let's say, deteriorating the water quality, its migration corridor barrier, sedimentation, greenhouse emission, biodiversity loss, land use change. Three Gorge Dam, it's the biggest dam in the world. It's the biggest hydropower plant we just saw in the very first slide. The entire community has to be relocated for the reservoir. It's a huge reservoir. You can go and you can read about the Three Gorge Dam, how it came into existence, all the engineering marvel there, and the kind of havoc it has, it has brought to the community. It's all available all over, the web as well. So, and some interesting facts as well. We can go and check it there. But whenever you come up with an hydropower facility, the community has to be relocated. It's pretty much the same with coal as well. Whenever you go for mining, if it's an open cast mine, you have to relocate the community which is living on top of that ground. Wildlife and aquatic impact. Reservoir water is usually more stagnant, as you can see here, than the normal water. As a result, it accumulates more amount of sediments and nutrients. And because of these nutrients which are accumulated, it leads to excess vegetation, excess of algae and aquatic weed. And as you can see here, these weed can crowd out other river animals and plant, and they must be controlled through manual harvesting. Right? And next is the life cycle global warming emission. Run of the river plants, as you can see, run of the river, that means where you are not constructing the dam, right? It's a natural flow that has been taken into consideration. And as you can see here, the emission which is coming from the run of the river plant, as you can see, 1 unit of electricity which is produced, it is about 0.1 and 0.3 pounds of emits between 0.1 and 0.3, roughly between that window of carbon dioxide per unit electricity, right? So per unit of electricity emits about 0.1 to a maximum of 0.3 pounds of carbon dioxide. Vis-a-vis, if you look at large-scale hydropower plants, it is about 0.6 pounds of carbon dioxide equivalent, all the gases together, right? So there is 0.1 and 0.6 times, 6 times higher. If not 6, even in like the most dense year is also double the amount, right? So run of the river, and that's why there is a huge emphasis on run of the river. Run of the river is not just good for in terms of this, because there is no dam in terms of GHG emission. It is also good for other things like the wildlife impact and the stagnant water problem, because it's on the, as the name itself suggests, run of the river. It's very much on the running river you have constructed this facility. Right? So all these environmental impact, biodiversity loss, and land use change are they don't really come into existence when we are talking about run of the river. And also because there are small capacities. Run of the river power plants, hydropower plants are small in capacities, right? So and especially if you are living in a high seismic area zone where, for example, if we talk about India, and we know that the Himalayan range, and this is where most of the rivers are originating, come up with a dam-based power plant system. And since it's the youngest mountain range in the world, so it is still very active. So all these hydrological changes, all these geological changes are still happening, and it is very prone to earthquakes. So therefore, having big dam-based power plant is, there's always a fear among the community as well if we come up with those big hydropower plants. But run of the river is what is recommended otherwise. So that was very quickly about the water-based. The next that we are looking here are the nuclear power plants. We saw in this training program in the last couple of lectures that how the world is now moving toward nuclear. Now, if you look at nuclear again, these are some of the very broad major units, processes, as we can see here. There is a contaminant structure here. Sorry, there is a containment structure here, which basically, as the name itself suggests, it contains, in case of there is any accident, it's a huge concrete and iron and steel have been put in here to ensure that the radiation doesn't leak, right? So there's a containment structure here. There are control rods, as you can see in here. There is this reactor, steam line. Where is the steam line? Yeah, this is the steam line here, right? And then we have the pumps that are flowing in here. There are generators, the electrical generators, turbine. Then there is cooling tower. And then these are the fuel rods. Where are the fuel rods? Okay. Yeah, these are the fuel rods, right? So these are the major components of a nuclear power plant. Other than that, there are many small power plants, and this is the PNID diagram. I thought, okay, fine, I didn't show you for the coal and the hydro, but just to give you a very quick glance of it, that these are the various kinds of control that are put in place. These are the various kind of system that we are looking at when you're operating a nuclear-based power plant, right? So various control systems are in place. Of course, nuclear power plant has to be doubly, triply, and four timely ensured that nothing goes wrong. For the very nature that the contamination here is primarily radiative in nature. It doesn't really hold within the compound of that facility. Now, if there is something goes wrong in a power plant, a coal-based power plant, it is very likely that it will impact majorly vicinity of people living nearby, 30, 40, 50 kilometers. Hydropower plant along the along the path of the river, right? But when it comes to nuclear, it sees no boundary. If there is a nuclear mishap, it impacts continents, from one continent to other continent as well. So therefore, nuclear is very, very sensitive towards such thing, such disasters, right? So we have to be very, very, very sure about safety when we talk about nuclear. Now let's look at, try and understand it as a fuel, as a facility. One thing as a fuel, second thing as an overall facility. Fuel itself does not generate electricity. This is important. Fuel may be very clean. Nuclear is a very clean fuel because it does not emit GHG. Hydro is a very clean fuel because it does not emit GHG as a fuel. But from that fuel, when you make electricity, you need a dam. I mean, otherwise, how can you produce electricity from water? Hydro-based. I mean, of course, you could say there are fuel cells and so on and so forth, but let's focus here that the hydro-based, big hydro-based power plant itself means the first image that comes to our mind is that of a dam. So the conversion part of it. Fuel may be very green, it's very clean, but when you convert it, then the entire supply chain, whether that is green or not, is equally important, right? So let's look at nuclear power plant for that matter. This is Fateh Birol's statement. He is the executive director of International Energy Agency. He says that alongside renewable energy efficiency, very important, and other innovative technologies, and nuclear can make a significant contribution to achieve sustainable energy goal and enhancing energy security. So the world is moving toward nuclear. When the ED of IEA says so, we are moving toward nuclear. We have to take him seriously, right? A nuclear power plant, it is often described as being free of greenhouse gas emission, and that's true for the nuclear fission reaction themselves. Only the process, right? The process, what is happening here in B, this whole thing, B and C. This is a control rod and the reactor, and this is the nuclear rod, K, the rod. So this structure, this part, I mean, look at it. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 such thing which is required, at least 12 such thing. And of this 12 thing, it's only this B, C, and K, 3 things combined together is green. Other than that, this cascading, right? Everything else, how it impacts, that is important, right? So green part is only this much. Free of greenhouse gas emission, that is true for the fission reaction, the reaction itself, whether heat is generated or from where the electricity will be generated. But here is a list of all the stages of nuclear power cycle at which greenhouse gases are emitted. Just like the coal mining, there is uranium mining, then The way we pre-treat our coal in terms of washing and cleaning, uranium has to be milled as well. It has to be converted into uranium hexafluoride. Then you enrich the fuel. Then the fuel is fabricated, the rod and all. Then the reactor is constructed. The reactor is again decommissioned after it has come to an end of its life, the reactor. It is carrying lots of emission. The decommissioning, how to decommission, ensuring that the radiation doesn't leak. That is the condition, right? Decommissioning of a coal-based power plant is relatively easy. Yeah, but when you talk about decommissioning a nuclear power plant, it is a tricky business. Then whatever fuel that has gone one cycle, you reprocess it and you try to reuse it. So there is a fuel reprocessing plant. How much of emission happened because of that? And the most difficult thing, that is the nuclear waste disposal. How do we dispose of the nuclear waste? Mine site rehabilitation, it's the same problem as coal. People, those who are displaced because of this mining, how are they being rehabilitated? And at every stage, the transportation. Nuclear fuel fabrication, fuel reprocessing, there are only few sites in the globe where they are done. That means the nuclear fuel, which is being used in multiple countries, how are they being, the traveling that they move, the continent to continent that they move, to ensure that, to keep the nuclear power plant running, they have to be taken into consideration as well, right? So this is the flow diagram, basically how it works, this nuclear fuel cycle. But today we are more interested, and then they generate a lot of tailings water as well, right? There are lots of water that comes out of the nuclear mining. So yes, in terms of emission, if you look at it, which currently means energy derived from fission, as of now, all of them are based on the fission reaction. Or the technology that the entire world use for nuclear power to derive is a fission-based process, right? It's not fusion, it's fission. We split it, and has a minimal carbon footprint of about 15 to 50 grams of carbon per unit of electricity. By comparison, nuclear has 15 to 50 grams of CO2 per kilowatt hour. That means per unit. Vis-a-vis, if it's a gas-based, you get 450. If it is coal-based, it is 1050. So yes, it is fairly clean that way. But then you have to say it is only the generation part that we are looking at. Now, if you look at why are we talking about nuclear fuel recycling, right? It is very important. And as you can see here, used nuclear fuel has long been reprocessed to extract fissile material from recycling. We try to, when it goes through one cycle, it is not completely converted. So you go and you try to, whatever has not been used, to separate it out and again put it as a fuel material. Also, when you do so, you generate lesser volume of waste. Otherwise, if you would have put it in the waste category, you would have generated a huge amount of waste. So the nuclear recycling processing is very important. And you'll see what are the problem with the waste disposal. That is another reason why we try to put it in recycling, and recycling as long as it's possible. And the recycling today is largely based on the conversion of the fertile U-238 to fissile plutonium. So this is the route. So when you recycle it, make it fuel ready again, this is the conversion that they are doing. So it's a facility where you are doing something. There is again a nuclear reaction which is happening to convert, to reuse the nuclear waste, right? And you could say 25 to 30% more energy from the original uranium is used in the process. When you convert it, you use it. You see several European countries, Russia, China, Japan, have policies to reprocess used nuclear fuel, although government policy in many countries have not yet come around to saying reuse it, and rather they prefer to put it to waste, because this is a very advanced technology. It is not a simple technology that everyone can have, right? And also not necessarily there's very few facilities who can do that, are willing to do it for you, or have the capacity to do it for you. And some countries are very sensitive about recycling or waste, how to dump the nuclear waste, vis-a-vis others who said, okay, fine, we have done it one time, we can now put it as waste. It all depends upon the policy of that country. As I told you, worldwide reprocessing facility, there are very few facilities which are available. There is one in Russia, one in Japan, UK, and France has it. France has one of the biggest facility, as you can see here, also because they are probably the biggest user of nuclear on date in terms of total energy that they use. And other, as you can see here, India has one, Japan and UK. So these are the only few countries, you can count it on your fingertip, 5 or 6, 4 or 5 of them, where we have, and this is the civic capacity, very important, because when we talk about nuclear it's come from civil, it comes from military use as well. So in terms of civil usage, that means for power, electricity point of view, these are the only facilities in the world where we are reprocessing it. Everybody else who are using is probably, I assume, are putting it in the waste category. Now, nuclear waste, very important. They are internationally described or categorized into these 3 categories, right? Low level waste, intermediate level waste, and high level waste. Generation, the volume generation, as you can see, the good part is that 90% of the waste that is generated is low level waste. 7% of the waste is intermediate and 3% of that is high level. That is in terms of the volume that we are generating. And what does it mean? It means that high level waste means 95% radioactivity is still there in that material. Low level waste, as the name itself suggests, only 1% radioactivity is left. All has been utilized. So you level it and then you dispose it, right? And after the nuclear fuel is used, the waste is still very hot and it is still very radioactive. So it has gone through the nuclear cycle, it has generated the heat, but and it is spent and it has come out of the reactor. It is still very hot and there are good amount of radioactivity still lying in it. So what do? Most of the cases, water is used. Water can conveniently provide both cooling and shielding. So after the rods are used, after the nuclear waste is generated, it is put in water for many, many, many years. Right? And it not just cools it down, it also shields, like all the radioactivity is also absorbed into it. So a typical reactor will have its fuel removed underwater. So when they remove it, it is done underwater. So look at it, the technical expertise and precision that is required when you are removing the fuel. It is done, it is removed underwater and transferred to a storage pool. Still with water, it is stored there. And after about 5 years of being storing there, it can be transferred into dry, ventilated concrete containers. How expensive is the disposal of nuclear waste? But otherwise, it can safely remain in the pool indefinitely up to 50 years, or you just let it be in the water for 50 years. At least 50 years, if you want it to be completely safe to be disposed. So this is one facility, as you can see here, they have, most of them are like, even this facility is underground. For here in Sweden, they have this facility on ground. And as you can see here, after the nuclear fuel has been used, they have been put in water like this. Now they will remain like this for many years. Many ways of disposal. All radioactive waste facilities are designed with numerous layers of protection to make sure that people remain protected. This is all about the waste disposal. Look at it, the kind of investment and the kind of resources we need just to dispose of the nuclear waste. Low level and intermediate waste are buried close to the surface. I mean, you dig a few meters of earth and you put it there and you bury it. Low-level waste disposal is not much difficult from normal municipal waste because it has just 1% left, so they can dispose it off on land as well. High-level waste can remain highly radioactive for thousands of years to come, and they need to be disposed of deep underground in engineered facility built in stable geological formation. So look at it, how complex it is. While no such facility for high-level waste currently operates. This is important. There aren't any. Their feasibility has been demonstrated, and there are several countries now in the process of designing and constructing them. High-level waste disposal, we don't know. The world as of now is not ready. Normally, what they do, as you can see here, this is one of the movement by Greenpeace. They are civil society, and they say that waste produced during the nuclear energy cycle remain hazardous for hundreds to thousands of years. Yet each year, millions of liters of radioactive waste used to be dumped into the sea, either from the nuclear facilities such as the reprocessing plant or from the ship at sea. They also use nuclear facility. For years, national government allowed this practice. It was done, they knew it is happening, but since there were no other way to do it or willingness to do it, it happened for many, many, many years, and a major threat to the environment and a potential health risk to millions of citizens and to the sea life. all the ocean life that is there. But now I think there is a convention, there is an agreement that has come. It's like an international multilateral treaty wherein some agreement has come in terms of what can be dumped, what can't be dumped. So if you're interested, you can go and check that. But as you can see here, that what I'm talking about is a very recent development. But before that, normally this is what the countries would use to do. They would take the nuclear waste and they will just dump it in the sea. And these are some of the nuclear power facilities. I think we have seen that earlier also, but you can see, sorry, this is the distribution of sea dumping site used for disposal of low-level radioactive waste. And it was before that I was talking about, right, where the countries would go and dump their nuclear waste in the sea. So these are some of the sites that have been identified that they would dump their nuclear waste in such locations. But this is not the case anymore, as far as I know, but you may check. So that was all about the conventional form of energy, which are not renewable. But now let's look at the renewable-based power option, like how green the renewable are. Even that need to be checked. It's not, as I told you, when you look at fuel to electricity, it is not just the conversion part. It is the entire supply chain. Everything that goes in has to be accounted for. And when we talk about renewable, the very first renewable are the solar-based power system. Now, we all agree that solar is a very clean energy, right? And we see how electricity is generated from solar. There are two routes. One is the solar thermal, and the other is the solar PV or the photovoltaic. Now, photovoltaic is often used, is the most diffused technology. Everybody uses solar PV to generate electricity from it. It's a photovoltaic effect as we know it. But how green is it that need to be checked? And how is the solar panel made? We understand, we have seen those big rectangular solar panels and the solar modules and the solar cells, right? And many of these cells come together to make a module. How is it made? That is important, right? How is it made? So let's have a quick look at it. Let me show you a video for that. Yes.
Freiberg plant, Solar World. At its Freiberg plant, Solar World produces multicrystalline silicon wafers for the photovoltaic industry in accordance with the highest quality standards. The preliminary products for solar cells are manufactured in 4 almost fully automated production processes: crystallization, brick production, wafer fabrication, and wafer finishing. Ultra-pure silicon is used as the base material in the manufacture of multicrystalline wafers. The feedstock is placed into a mold made of fused quartz. With a load of up to 600 kilograms of silicon, the mold starts out on its way toward melting furnaces. The fully automated process maintains the highest purity standards and conditions. With crystallization furnace temperatures reaching more than 1,400 degrees Celsius, the silicon melts within 20 hours. After 3 days, we have produced a multicrystalline silicon ingot measuring 84 by 84 centimeters. The efficiency of the subsequent solar cells depends entirely on the quality of both the melt and the crystal structure. Upon removal from the mold, the silicon ingot is transported from the crystallization center to the ingot store. While continuing to cool, it remains in an intermediate buffer zone, awaiting further processing. The crystallized silicon ingot is then removed from the ingot store and hoisted into a so-called briquetter. This high-tech machine divides the ingot into 25 equal-sized square bricks in a cutting process which, owing to silicon's special material structure, poses a unique challenge to the tools involved in this process. A view inside the briqueter shows a cutting head with numerous deflection rollers, over which a special wire runs. The arrangement of the rollers ensures that the wire saw produces a matrix corresponding to the cross-section of the bricks. The cutting head slowly sinks downwards, causing the wire saw to cut through the silicon ingot. With rapid to and fro movements, the slurry, which consists of a mixture of silicon carbide and polyethylene glycol specially developed for the silicon cutting process, is kept in motion. The cutting process, during which the silicon ingot is cut into 25 bricks and side parts, so-called tops and tails, are removed, takes approximately 7 hours. Then it's time for a wash. Fully automated computer-controlled conveyor lines transport the cut ingot pieces to the ingot washing system. This latest generation cleaning system resembles an oversized dishwasher. First, high-pressure jets blow a cleaning fluid around the silicon ingot. A blower subsequently dries the bricks. 15 minutes later, a robot picks up the bricks one by one, measures their geometric parameters, and passes them on for marking. High-tech measurement devices weigh and measure the silicon bricks and scan them using infrared rays to determine the quality of the silicon crystals. Short and efficient routes, these are the defining features of our water production workflow. As soon as the bricks are catalogued, a fully automated shelving system transports them into the intermediate store. The storage location is chosen such that bricks of the same quality are stored together. The system also combines varying brick lengths to form a uniform machine size, a so-called batch. Following a thorough sorting of the bricks, they are now ready for the next processing stage. Via the fully automatic shelving system, the pre-sorted silicon bricks are then transferred to the wafer fabrication stage. The bricks are bonded to both a glass plate and a carrier panel, a technology that has been developed and continually improved by SolarWorld's experts. In the wire saw section, which comes right after the bonding center, another wire saw process is used to cut the bricks into thin discs, the so-called wafers. The high-tech saw is equipped with 2 large track rollers. In contrast to the briqueter, a special wire of roughly 700 kilometers length runs across it at high speed, creating a rotating wire field through which the silicon bricks are pushed. The wire transports slurry. Its fine particles slice the silicon brick into wafers that are approximately just 0.2 of a millimeter thick. After approximately 8 hours, the plant has produced between 2,000 and 3,000 wafers. As one of the largest photovoltaic companies, SolarWorld not only produces wafers for its own solar cell production, but also for sales to customers worldwide. The fourth and last production stage in the manufacture of multicrystalline silicon wafers begins in a large cleaning plant. The sliced bricks, which are bonded to carrier panels, are pre-cleaned in baths to remove all slurry and saw residue. The plant then automatically transfers the bricks to an adhesive removal basin, where the bricks are separated from the carrier panel, resulting in approximately 0.2 millimeter thin silicon wafers. Next, the wafers are isolated and run through further cleaning lines, various surfactant and water baths, and the subsequent drying process ensure optimum surface cleaning. All wafers are then measured by fully automated sensors and cameras and graded according to their thickness and surface quality. As base elements in solar cell production, multicrystalline wafers are subject to very thorough final inspections. Aside from automatic testing procedures, the trained eyes of our staff also help ensure the high-quality standard of our products. Finally, once they correspond to all our strict quality requirements, the wafers qualify for the Solar World logo. Securely packed, our wafers are then shipped all around the world. Again, automated processors guarantee maximum punctuality and flexibility. In as little as 8 days, ultra-pure silicon has been transformed into multicrystalline wafers for the photovoltaic industry, applying fast, energy-efficient and cost-effective processors around the clock. Each day, wafers with a total capacity of around 1.5 megawatts leave the factory, enough to cover the electricity requirement of 1,600 people and take another big step along the way towards worldwide, independent, environmentally friendly and secure energy supplies. This is what we at Solar World stand for. We turn sunlight into electricity.
Right. So that was very briefly about solar power options. So you saw that the manufacturing of the solar panel is a very, very energy intensive process. You start with silica, you melt it, you make the wafer. Even this one single process that they showed you, it took them about 8 days time for this multicrystalline system, right? So now let's look at and study this. I mean, in absence of this wafers, which we call as, then they are cut, made into cell, and these small cells are then put in modules, and then we get the solar module, the one that is sold in the market, where it is like put in a glass cascade and all those stuff. So yeah, so let's look at the solar option. So this is how solar-based power plant work, or solar parks. Basically, you have the panel where you collect it. This electricity is primarily DC, then it is converted into, you see an inverter here, it is converted into AC because that's how the power is transmitted. Sometimes we do bring in storage, transformer and all those stuff. This is common, that happens in all the power plants. When it comes to consumer, they monitor it. There are some control systems put in place. This one doesn't have battery. Sometimes it is stored in battery as well, because some amount of energy has to be stored in battery for emergency situations, for weather conditions. It could be very sunny, but what if it gets cloudy after some time? So you store the battery, or for nighttime. So daytime, you keep on working as the sun is there. And at nighttime, when the sun is not there, then to lit up the load wherever it is required, the batteries are kicked in, right? So sometimes we couple it with battery as well. Now, batteries, as you understand, has its own merits and demerits, the environmental impact of it primarily. So if you look at the solar power plant, how it is, if you want to do a life cycle analysis for it, if we see that whether over its entire life, this is what life cycle means, over its entire life, and normally we assume that the solar module that we see has a life of about 25 years, 20 to 25 years. So even if we assume, let's say 25 years, that is the maximum thing, how much of energy has gone into it to manufacture it, to source these materials, the emissions that has gone into it, and how much is it produces, right? How much of electricity it produces over its lifetime, and all the emission and everything is loaded on that production thing. So if it has produces X units over 25 years, then it is loaded on 25 years, all the X unit is loaded, all the emissions are loaded for those X units, and per unit is calculated. Simple, right? But processes, if we look at, it starts with quartz mining. We saw that. The metallurgical aspect of it, then you make, if it's a crystalline, you work like this. If we make it from the wafer part of it, multi-silicon, it works like this. So anyway, there is a crystal formation, ingot formation, wafer formation. Then you put it to cell, put it in frame to get the module. And then eventually you get the PV system. So this whole process of manufacturing the PV itself is a very energy intensive, it's a very emission intensive as well, right? Process that is there. This is one type of module, the solar cell that is made. And this is other way. One is with silica and other, this is other technology. They call it CDTE. So this is another mechanism by which you could develop it, right? So these are thin film, which is popularly known as a thin film PV. So this is the process which is involved in the manufacturing of the PV system. In both the cases, you see it starts with it's mining. Here they have not said mining, zinc ore, but even zinc ore is coming from a mine, and this copper is also coming from a mine, right? So starts with a mining, from mining till the PV system, the module that we see. Input material, output material have to be put in place when you do the life cycle analysis, right? So raw material acquisition, there is some amount of energy going in and material going in, water, soil, air, which is required, production, component, assembly, operation and maintenance. And then there is disposal. From raw material acquisition, that means you may start from mining, or you may start from gate, that means it has been delivered to you. And then you produce it, that means those ingots that are produced in there, the components, the wafers, putting the wafers together, making the module, then you operate it in the plant. There is a transport part also available, but as you can see here in this particular LCA, they have not considered the transportation, right? And then they have the operation and maintenance when it is in the field. And then after 25 years, let's assume that the life of that solar panel is 25 years. How do we dispose it, right? And at some point of time, after it is used, we also recycle it. That the silicon, all the material are very much there. It could be used by the plant. They may pick it up the way I discussed this buyback policy of the mobile phones. They may buy it back to you. Some kind of a mechanism is put in place so that we can recycle. Right. So as you can see here, the life cycle atmospheric heavy metal emissions from PV system. It's various kind of emissions that are happening. Right. Efficiencies and ribbon and multicrystalline. So all that things are given to you, right? So what kind of heavy metals are there? What kind of emissions are happening under various conditions? Cases are given. So what I'm trying to say here is it's not all green. The production part is certainly green, but there are emissions that are happening, not just in production phase, also during it usage phase, right? So solar is green, solar is clean, but it is important that we look at the hint side of the picture as well. Right, so as you can see here, solar photovoltaic, it's about 40 grams CO2 equivalent per unit of electricity, which is produced, right? And as you can see, and if we divide it, of course, with respect to coal, it is very clean. So I'm not saying that it is not all clean. It is very, very clean with respect to coal. But look at how this is distributed, how this 40 gram is distributed. So majority of that is in the production phase, the raw material extraction. Plant generation, system operation, maintenance, all the arrangement that you do, all the controls that are put in place, their share is about 25 to 26%, right? Generation part. Coal, vis-a-vis coal, because coal generation part is where all the emissions are happening. But this, I mean, if the percentage, this 1000 grams of CO2 equivalent per unit, which is coming out of a coal-fired power plant, raw material extraction is less than 1%. Mining, they have taken it here, right? So you have to see how we have placed the various processes, right? So they have taken this mining, preparation, transportation, combustion, operation, and maintenance here. Generation and maintenance only is considered here. And then they have given the comparison. That's how this 40 gram is distributed, how this 1000 gram is distributed between various processes. So decommissioning, it's very little. This is where the major emission is coming from in a coal-based power plant, right? And here it is the preparation of the module, right? So this is it. But in totality, yes, with respect to coal, as you can see, photovoltaic have very little emission. Yes, so I have already shown you how the modules and wafers are produced. And of course, after being produced, they have to be there. They need heat treatment as well on both sides of it to give strength and efficiency to them. So that was very briefly about solar power. Now let's look at the wind power plant, some of the renewables as we discussed. So wind, as you can see here, there is very simple to look at. Here is wind which is blowing. There are the rotor blade. They are made at a certain angle. Then there is a gearbox. That's where all the magic happen, right? So wind the mechanical energy of the wind or the kinetic energy of the wind is converted into the mechanical energy of this blade, which is transferred to the gearbox, rotates the turbine, and this is where electricity is generated. And then there are power cable that brings the electricity down, and there is a transformer where it is matched, the frequency and everything, and then it is fed to the grid. Simple as you can see it. As you can see here, wind turbine is essentially dependent on three framework: the production, manufacturing, the design, size, and the wind condition. It is possible to calculate the carbon payback. We will be studying about payback and all these things in the next class. Just hold that thought for a moment. For wind turbine, the length of time it takes for a turbine to produce enough. This is what payback is. I'll skip this definition. Let's not talk about payback at the moment. We will study it a little later. But you can see here one study put that payback time at even 7 months. Not bad considering the typical 20 to 25-year lifespan of a wind turbine, right? So it is the take-home message is that whatever energy and carbon that we have emitted, it could be payback, like it could be recovered in just 7 months of its operation. After that, the energy that it is producing is more or less all clean and green. And yes, and they are fairly better off than with respect to solar as well. I mean, all the renewables are better than the fossil-based system, but between solar and wind is even more cleaner than the solar technology. It as you can see here, it doesn't involve the formation of the wafer. If you look at the previous slide where the formation of those solar module is an energy intensive process, it involves mining and all those stuff. Here also, of course, to make the blade, there are a lot of research happening in the material that are used for formation of those blade, the coating material that is used on that blade so as to increase its life. So a lot of research is happening there, but it is not as intensive as the solar module is, because for the solar thing, you need that semiconducting material. Need those kind of materials, right, which have the photovoltaic impact. But wind, you can try new materials as well. You need certain strength depending upon what kind of wind that we are looking at, what kind of shear the wind is produced, and you can produce different kind of wind materials. So there is a scope to do it, unlike in solar where you are limited. The very fundamental principle require that the material that you are using, they have to be of certain type, like silica. So wind power plant, there is wind plant component manufacturing, resource extraction, raw material processing, component manufacturing. And as I told you, there is a scope here. You may change the material. And when you change the material, it could be that you are no longer extracting it. It could be made out of completely waste material. For example, I'm just giving you an option, a scenario that you use metal blade. Let's say we use here steel blades, for example. And one thing is that the steel is produced after the extraction of the iron ore and then steel is made. The other thing would be that the material that I'm using are discarded steel from some decommissioned plant or whatever, right? And I used it. So if I used a recycled material, my footprint, the embodied emission actually goes down. One good thing about this life cycle analysis and all the methodology that we use is when you use a waste material, the embodied emission on that waste material is taken as 0. And that is the benefit of CCUS. When you use CO2 and you put it to some use and you make any product out of it, let's say you captured CO2 from a power plant and you made maybe a fuel because there is carbon, or maybe a plastic out of it, any sheet, a plastic, any material, any organic material, right? So what is the embodied energy of this CO2? What is the embodied emission of this CO2? Now, since it is waste, we don't load it with any embodied energy or embodied GHG. The reason for it is because I have taken this CO2 from the stack of a power plant. So all the emission that has happened, all the energy that has embodied is for the product. So all the emissions and all the energy is loaded on the product, and the product of the power plant is the per unit of electricity, the amount of electricity it has produced. No, we don't set up a power plant to produce flue gas. No, we set up a power plant to produce electricity. So all the emissions, all the intensities, resource, is loaded on electricity, and the waste, which is CO2, is not loaded because it is a byproduct, or it is a waste product basically, right? So that's why when you capture this CO2 and you put it to some use, you make a lot of carbon benefit in terms of accounting. Because here, whatever product you are making is free from any of the embodied emission or free from any of the embodied energy, because you cannot load the same energy on two different things. It's just like the law of conservation of mass or energy, right? So that's the reason when you try to capture things, all the methodologies that we have developed to account for the carbon emissions or carbon accounting, waste is that's why we call waste as a resource now. It is a resource. And if you put it to some use, it comes with an absolutely zero carbon loading and zero GHG loading, right? So that is one benefit. So we have resource extraction, processing, and material. So you may think of new materials of making these wind turbine blades. Then there is construction. Some amount of civil construction is also required. We will be mounting this windmill, installation, commissioning, and transportation, operation, and then there is end of life. In the figure itself, you can see it's relatively simpler than even the solar thing. Environmental impact, wildlife impacts are there, land use change are reported. You see that the local species of population, birds and bats, and blade turbine rotate in high speed and high pressure around the blade shift. The birds and the bat collide with the blade, I mean, because of the disturbance that they create. Similarly, land use, yeah, whether you have put it on the flat ground or you have put it on the hill. And that's why even to bring down the impact of land use change, you see people are now going offshore. We are going inside the ocean to extract the wind speed, also because the wind speeds are higher there. And as you can see here, but it requires more space than the land-based ones, as the turbine and blade tend to be larger. And then, as you can see here, wind turbines and their supporting infrastructure don't take up much physical land space. However, individual turbines need to have sufficient amount of space between them, which can add up to larger or large-scale wind farms, right? So in terms of impacts, environmental impact, whatever we have studied so far, environmental impact of wind probably is the least. Of course, whenever you are bringing in any impetus into a form of any energy or change into nature, there has to be some some amount of entropy to be generated. So you do see some impact on wildlife, you do see some change in land use change, but relatively it's so far the least. And the last that we are studying today is the bio-based system. That means the biomass-based power plant and other derivatives. And as you can see here, across various impact categories, as I have told you, I don't know, I think I have. Yes, so let's, yeah, look at this one. Biopower. Now, whenever we say biopower, one thing which is often said is that it's a carbon neutral source, right? Which is true under given certain conditions. That's why we say that is biopower carbon neutral? The answer is it depends how you are using it, right? With respect to fossil, of course, because majority of our energy today is fossil driven, so the reference point always will be fossil. But with respect to fossil, yes, it's very green. But whether it is carbon neutral or not, it depends upon and comes from a very simple equation. The equation is very simple, that the total amount of biomass that you are extracting or using, whether you are putting the same amount of carbon back into locking the same amount of carbon into trees and other sources or not. Since it's biopower, it basically means forest, trees, agro residues, so on and so forth. Basically, everything which is which perform photosynthesis, right? So the idea is the source could be called as carbon neutral, or the power plant could be called carbon neutral only when the rate at which I'm extracting the plant, let's say I'm a wood-based power plant, then the rate at which I'm using wood, whether I'm replacing or locking the same amount of carbon into the woods or not at some place. So what they are doing, they are combusting wood at one point of time, whatever, any technological treatment, could be combustion, pyrolysis, there are many routes. So when I'm subjecting it to a treatment, certain amount of carbon is going into my reactor. Whether the same amount of carbon I am locking in the form of wood in some forest or not. The forest could be in my premises, it could be located outside my premises. I try to keep it close to my premises, because if it is really far off, then I am actually spending a lot of energy in transporting it, right? So decentralized is the answer. That means but keep it close. We hear a lot about ethanol. Many countries are using ethanol as a fuel to run their IC engines, to run their car. Brazil is one such country. US is one such country, two major user of ethanol, right? Brazil makes ethanol from sugarcane and US makes ethanol from corn, right? And both of them, and Brazil started way back in the 60s, early 60s. US came into existence in last couple of decades only, right? But if you look at the Brazilian ethanol system, because when Brazil came up with this ethanol plan, their idea was energy security. They wanted to be energy independent. That was a very good idea. And therefore, they promoted sugarcane plantation and making most of the country. If I talk about Indian biofuel policy, it very clearly says that anything which is food grade, anything from which food can be extracted, will not be diverted for fuel. So therefore, sugarcane to ethanol is an absolute no-no. It cannot happen in India until they brought in some change. They brought in the change. I'll discuss about it a little later. But up until 5 years back, this was not the case. Anything from which food can be made, any food can be generated, will not be diverted for fuel production. So there was either ethanol from sugarcane or from corn was out of question in this country, right? So now let's get back to it. So when Brazil started this ethanol plant, so they did plantation in one part of the country where it was most suitable, water was there, the land was fertile, and based on that, they identified those locations and the plantation was done. Now, after the sugar cane is produced, you have to treat it to make ethanol, right? You have to basically, the process is called fermentation. So you take the juice, the sugar cane, you extract and take out the juice, you treat it, you make simple sugar out of it, and then you ferment it, right? So from simple sugar to fermentation, needs another set of processing. So they came up with those factories, and then the alcohol has to be distilled. So let's call the entire infrastructure as distillery. So there is a plantation facility, there is this fermentation facility, and then there is a distillery facility. So plantation where plant is done, fermentation where alcohol is formed, and distillation is where you separate out the ethanol, fuel grade ethanol, so that it could be used. And then it's the same process. It goes to the various dispensing station from where you fuel your vehicles. There are certain engines in IC engines that are available in Brazil, which run up to 100% ethanol, like purely ethanol, up to E85. That means the fuel has to be 85% ethanol and rest 15% has to be fossil-based or diesel or petrol. So all sorts of mechanisms have developed in that country. But, late in last 15, 20 years, when we started talking about carbon neutrality, that was a very good plan that Brazil did to bring energy security in the country. They were producing their own energy through sugarcane, right? But when they sat down and to see that, let's see whether our ethanol is carbon neutral or not, then one of the major, still is a good source, but when they did the entire supply chain and it was studied, and we found out that the transportation, because the plantation was happening in one part of the country, the fermentation was happening in other, the distillation is happening at some other place, and it is used and it is transported differently, right? So the transportation of this raw material to the finished product was taking a huge amount of energy. So therefore, there is a lesson to be learned. Of course, it's a very good example to bring in energy security, the way the energy market is going through so the uncertainty phase right now. So it gives a lot of confidence to the country, which is a very good thing, no doubt about it. And when they started, nobody was talking about carbon neutrality, right? So Good. But now when we are talking about carbon neutrality, it is very important to plan very wisely. Otherwise, it may happen. And some studies do claim that the ethanol that Brazil is producing in totality is a carbon intensive, it is a net carbon positive. Some claim that no, it is not. So all sorts of literature is available. But the question here is that now that we have a lesson, one thing we cannot ignore that yes, this ethanol does a lot of transportation before it reaches your, we call it the well to wheel, right? So therefore, as a country who are now planning to do it, we should take the lesson from Brazil and we should learn that it is very important that your plantation should be close to your fermentation facility and it should be close to your distillation facility. Dispensing, of course, has to happen across the country. You cannot say that people in X location will be using more car and people at Y should not be using car. We cannot do that. That part is beyond our control. But at least these three things, from cultivation, like agriculture, till distillation, should be planned accordingly so that the transport, the carbon or the energy or the emission that you embody because of these transportation should be minimized, right? So that is one thing about carbon neutrality. And in total, yes, it is neutral because through photosynthesis, it takes in CO2, and when it is combusted, it puts back CO2 into the atmosphere. To make it carbon neutral, the rate should be same. If you want something to be zero, then on your left hand side and your right hand side has to be same. Otherwise, it will not be neutral, right? And as you can see here, normally this is how we put the boundary. This is important. Every process has a boundary when you do calculate the energy or the emission that it has embodied. So there is energy which is coming in, there's material, there's mass, there's energy which is coming in. You put in the production phase, cultivation, harvesting, and it's up to you. When you put all these things, you do put in, like, for example, you may put in pesticides, insecticides, fertilizers, all those things are important. Harvesting machines that we are using. So cultivation, agriculture itself has become a major emitter. This is nothing but agriculture. Right? So agriculture in totality is becoming more and more energy intensive as we are making it more and more mechanized. Right? So we are increasing the carbon intensity and the energy intensities of our food as well, for that matter. Right? And then it is transported, whether you are using it for electricity or you are using it for fuel. So when you're looking at an alternative to fuel, biomass is the only solution. When you're looking at an alternative to energy, yes, we have solar, yes, we have wind, but with wind and solar, we cannot produce fuel, liquid fuel or gaseous fuel. For that to do or to retrofit whatever is the existing engines that are there, they won't to become obsolete. But that means people will keep on using it for next 50 years for sure. That doesn't mean that for next 50 years we should not do anything about it. Let's make our fuel clean. In the same IC engine, can I replace a part of it with a biofuel so that the emissions could be reduced, assuming that the relationship is linear? So therefore, all these research is happening, all these interventions are brought in so that we could make our fuels, fossil fuel also, clean. Threat from bio-based power plant, yes, deforestation, because we need land to grow such fuels, such crop. So there is a threat of deforestation, pollution, of course, outside the country. There are liquid, solid and gaseous pollution that happen because of processing of such fuels. And water use. Water use is very important. Now, plant requires water to grow. So we are putting our water toward our fuel generation as well. It is important whenever you grow something. That's what I said, that our agriculture have also become very resource intensive, become GHG intensive as well. Resource means the kind of water that we need. We saw the example of cotton the other day, that it's a very thirsty plant. It requires a lot of water to grow. So when you grow cotton and when you export cotton, for example, it is not just the amount of cotton that you are exporting, it is also the amount of water that you are exporting with that commodity. Similarly, food as well. Rice, wheat, maize, millets, whatever you are growing. It's not just, so when we sell that product or that harvest, it is not just the mass that we are holding. It's not just 1 kg of millet. Along with that 1 kg of millet, we are giving away so much amount of water, so much amount of nutrients, everything accounts for, right? So that is very important. And at the end, I would like to compare it with the different fuel options, as we can see in here. Over the life cycle emissions per unit of electricity that it is producing, how much amount of GHG, because I'm saying CO2 equivalent, that is the GHG potential of all the gas put together on the scale of CO2. So photovoltaic stands here. This is the concentrated solar PV. Sorry, not PV. This is the concentrated solar power, which is we use the thermal energy of power itself to generate electricity or heat. So as you can see here, the life cycle emissions are much lower, but somehow it's PV which is being promoted more. Geothermal, wind-based, wind offshore, onshore, biopower. So these are the renewable options. And you can see all the renewables are lower than these conventional technology. Nuclear, of course, is placed at a very lower emission category. But then, as I told you, there are other very complex problem with nuclear that must be considered, right? Simply because it has a lower GHG potential doesn't mean that we count nuclear as an absolute clean and safe energy. Then we have gas systems, as you can see, natural gas-based system, coal-based system, combined cycle. I explained it to you yesterday, how it is different from how it is lower than the conventional power plants. And then we are going for advanced technologies of supercritical and subcritical and the supercritical technologies of coal-fired power plants. So this is the relative, that's the bird eye view of all the emissions that are coming from different sources. Okay, the same thing. Yeah, so with this, I end my presentation. If you have any query, I'll be more than happy to take it.
Ma'am, there are some queries at the chat box. You can.
Yes, I can see that. Okay, so I don't know what's the question about the dam thing. I mean, for what slide it is, the dimension of the dam, how much this affects the phenomena greatly. I can give you, there are lots of research that has happened and it's there in public domain, and IPCC has also reported it. So we will share with you the IPCC reports wherein they talk about what size dam brings in what kinds of emissions, right? And relative, I have given you like the run of the river emissions are relative much lower than that of the big capacities. But the report is there and I'll share it with you because you're asking for the numbers and you could get those numbers. The entire accounting and registry business is all about giving number to these phenomena. All the phenomena that I have discussed today: deforestation, land use change, threat to wildlife, biodiversity loss, ocean acidification, rise in temperature. I assume all of us know this. The whole question here is, what number? How do we get to these numbers? What are the impacts? How do we do that? So it requires very extensive study. And if you want to see the change or drop in the biodiversity, it cannot be done in 1 year's time. We have to study it for a longer time. To track the change in loss of biodiversity, you need to know what is the biodiversity today, tomorrow, day after tomorrow, 5 years, 10 years, 15 years. So these are time-consuming processes. People have done it, and the data bank is there. I'll share with you all the data banks that are there in public domain and the other ones as well as a complementary study material to all of you. Then, yes, the same question. The second question is also about the storage thing. Do we have the data? How do we determine it? All the data are there. Yesterday, you did a quick hands-on in terms of how you select those data and how it is linked, right? But those data sets, where you can get it and the references for it, I understand majority of you are asking for it and we will share it with you. Hold on, about CCUS, we have one entire day dedicated to CCS. You will be hearing about it, but of course the costs of electricity is higher. How much? It depends upon the economies of scale, at what scale we are operating. CCS in terms of any commercial power plant, to the best of my knowledge, is not there. Some plants are demonstrating it, but it is for demonstration purposes only, right? So that the lessons could be learned, and based on that, the policies could be framed and the pricing could be decided. Does CCS makes coal power plant less efficient? How much energy is needed for capturing CO2 from CCS? Yes, the answer is it depends, right? Of course, the price would be higher for sure, because you are bringing in one extra step in your process, right? Does it make the plant less efficient? Maybe. Again, it depends what scale we are talking about and what technology we are using to capture the CO2. There are many technologies. There are membrane-based technology. There are amine-based technology, chemical technologies. What technology we are using? What kind of wastewater they are generating? And how we are treating the wastewater. So it depends. And how much energy is required? Yes, CCUS, there is an entire, as I told you, please hold on that thought. CCUS, there is an entire day dedicated to it, right? So we'll be hearing a lot about CCUS. Yes, I could see, Abira, your hand is up. If you have any question, please ask.
Okay, thank you, doctor. And my question is on hydropower. As we see, hydropower is the power that we can get from the water, which is repeatedly we can get from hydrological cycle. Is there? I confused that whether this hydropower is renewable or conventional. Where is the classification for this hydropower? One is this. On the wind power, the payback time, as you told us, one scholars show that the payback of this is 7 months, but it is better if we take 20 to 30 years. So what is the cause for this much gap between the time we can take for best payback and the research? Thank you.
Thank you. Talking about water, whether it is renewable or not, or conventional, it is renewable. If you look at the source, technically it is renewable. Water sources, water-based thing, it is renewable. It's, as you rightly said, that there is a hydrological cycle. You get the water and it is renewable. The second question was about emissions. Now, the question is, with respect to coal, yes, it is green. Individually, whether it is green or not per unit of electricity, how green or how gray or how black? If you put up a scale here, that depends upon your scale. I give you an example also that if you are constructing a big dam and you are generating very little electricity, and then if you put a life cycle around it, then the product that I'm taking is electricity. There's only one product that I'm considering, yeah, which is electricity. Now I load every emission that is happening from the dam on that unit of electricity. Now, if I'm producing more electricity, as you understand, the equation is emission per unit electricity. So the emission is in the numerator, and in the denominator, I have electricity. It simply means if I produce more electricity, the ratio would be small and the footprint of my electricity will be less. So therefore, there need to be a balance. You have to see, that's why hydro is a very tricky business. And I also told you that it depends upon the meteorological region where you are in. Canada gets a lot of benefit from the hydro energy power. Their emissions are very little. One, because they have very big capacity hydropower projects. And second, because they are relatively cold country, the emission and the vegetation growth in their dam is very little. The same hydropower plant, if I bring it to India, or if I take it to other tropical countries, the emissions would be much higher. I'm just talking about the dam at the moment. I'm not talking about the water flows down and yet the electricity is produced. The dam itself. So hydropower, the tipping point or the unit that could take you to the green side or it could put you in the emitting side is the dam. How you are operating the dam, how much water you are holding, how much of concrete has gone in making that dam also. Right? So all these things are considered. Now, if there is a dam and this dam is giving you other product, there is electricity that you are using and you are using it as a water for irrigating your field. That is also a product, irrigation purposes, right? Then Now look at it. Now, when you do the life cycle calculation, the emission remains same, which is coming from the dam. There is a dam. Okay, the emission remains same. The kind of vegetation which is growing, it's same. It doesn't matter to the algae or to the vegetation which is growing. It doesn't care whether the water is used for electricity or for irrigation purposes. Okay, now when your life cycle calculation, you are accounting that the product that is from this dam is electricity plus irrigation. Okay, in that case, in your denominator now, there is electricity and then there is irrigation also. So per unit of the product, it is difficult. It is difficult again, you need some conversion factor because in your denominator, there are two different things. There is water, which is like in terms of liter, and then there is electricity, which is in terms of joules. So you have to bring in a factor so that you could combine them, right? Or you do it independently and then say what is the per unit or per liter, whatever it is of your emission is loaded, right? So when you do this carbon accounting, there are methodologies, and therefore it is important that you follow the methodology. All of us could bring in multiple product and it could compare it. No, please follow the methodology. We will share it with you, the methodologies toward the end of the coursework. All the study materials will be given to you. Therefore, I'm saying that when you see these numbers, it's a new phenomena. It is still evolving. The whole life cycle thing is still evolving. We are coming up, you see such and such version 1, version 2, version 3. We go, we learn, we come back and we bring the changes so that we could improve upon, right? So whenever you see these numbers, study the formulas. What formula they have used, how have they calculated this number? It is important, right? So study that. And what was your last question? I forgot. You asked something else that was about hydro and this. Yeah, can you just repeat?
Wind, yeah. Wind.
Yes,
power.
very good. Yeah, wind power, absolutely. When you calculate payback period, yeah, government policies are equally important. What kind of support is given to you? One is in terms of net amount of energy that you have produced. We will be saying it. All the payback calculation we will be doing in the next class, 15 minutes from now. The depreciation cost, the capital cost which is there, right, that you have brought in. And if there is a market mechanism, you rightly said, in certain countries it is as small as 7 months, and for others it could be as high as 7 years, right? So for example, I could give you the capital cost that is there, the investment that you have done in erecting that infrastructure, right? I tell you, in India, in late 80s, they bring in, to promote wind, they bring in a policy that says 100% depreciation. That means at the end of the year, all the investment that you have done is depreciated is zero. What does that mean? That means you don't have to pay additional tax or additional revenue for that as an asset. It is no more an asset for you. It is all depreciated in just 1 year's time. So that gave a major push to all those who were, all the venture capitalists and all those, those who wanted to put their money to some use, they used it extensively. And that's how the wind power grew a lot. So it is, when you talk about the payback period and everything, in an indirect cost or indirect support or as a major push, the policies, the banking and all these market mechanism also plays a very important role. Right, so we will take a quick break. We will come back to this payback period in our next class. We will be studying all that in the next class. Okay.
Thank you very much, Doctor.
Thank you. Thank you. So let's break and meet after 15.